8.4 Part 2. So we're going to start talking about the inverse properties of logarithms, and of course a logarithm is just an inverse of an exponential function. So in order to, well, quote, cancel out a logarithm, what we have to do is we have to raise it as a power of the base of the logarithm. So for instance, if I have, let's say log base 3 of 9, we know that that's equal to 2 because that's the exponent that it gets raised to. Now, if I just wanted to cancel out the whole log base 3, what I would do is I would take 3 raised to the log base 3 of 9, and what that would do is that would give me 9 because the 3 raised to the log base 3 would cancel out, and I'm just left with whatever that value is. So looking at example 3a, we have 10 raised to the log of 2.3. Now, because there is no base there, so it's just log, that's the common log, which means log base 10. So really it means 10 raised to the log base 10 of 2.3. Well, what happens is the 10 and the log base 10, or the common log, cancel out, and we're just left with the exponent. So 10 raised to the log of 2.3 is 2.3. Okay. And then for b, we have log base 2 of 8 raised to the x. Well, this is a little more complicated because my log base 2 doesn't match up with the 8. However, 8 can be written in exponential form, okay, as log base 2 of, well, 8 is equal to 2 cubed. So that would be 2 cubed raised to the x power, and then I use my power of a power property. That was the same as 2 to the 3x power. Then my log base 2 and 2 cancel out, and I'm just left with that 3x. Okay. All right, and then example 4, finding inverses. So to find the inverse of the function, okay, so the definition of a logarithm, the inverse of y equals log base 1/2 of x is y equals 1/2 to the x power. Okay, so we're talking about the inverse of a logarithm function. Y equals log base 1/2 of x. The inverse is y equals 1/2 to the x power. So you're just basically turning that into an exponent. Okay. So then for a little more complex one, what we do is we would switch x and y, okay, just like we do for other inverses. So x equals the natural log of y minus 2, okay? And then we would write that in exponential form instead. So in order to cancel out the natural log, I have to do e to both sides. So e to the x power equals e raised to the natural log. Well, that cancels out the natural log because remember, e is the same as, that's our natural number. Natural log is the same as log base e. And we're left with e to the x power equals y minus 2. And then all we have to do is solve for y. Well, in this case, solving for y just means adding 2 to both sides. So e to the x plus 2 equals y. So therefore, the inverse of y equals the natural log of x minus 2 is y equals e to the x plus 2. Okay, now the last thing that we're going to talk about in 8.4 are the graphs of logarithmic functions. So the graph of y equals log base b, okay, of x minus h, okay, so there's our h again, plus k, and there's our k again. So h and k, that's going to represent h is our horizontal shift, and k is our vertical shift. Now, because a logarithmic function is an inverse of a exponential function, that means that now instead of having an asymptote at k, we're going to have an asymptote at x equals h. So instead of a instead of a horizontal asymptote like what we had in our exponential functions, we have a vertical asymptote for our logarithmic functions. So our logarithmic functions always have a vertical asymptote at x equals h, whatever that horizontal shift was. The domain is x is greater than h, okay, so x is all values greater than h, so now we have a limited domain, and our range is all real numbers. Okay, so the inverse of our exponential functions. Remember, our exponential functions had a domain of all real numbers and a range of y is greater than k. Now we have a domain that's x is greater than h, and the range is all real numbers. And if b is greater than 1, so if our base is greater than 1, it moves up to the right. If 0 is less than b is less than 1, so in other words, if the base is between 0 and 1, some sort of fraction less than 1 but greater than 0 still, it's going to move down to the right. Okay. All right. So now example 5, graphing logarithmic functions. So for a, we have y equals log base 1/2 of x minus 2. We're going to plot a couple of convenient points, so we can pick any points we want. So they picked 5/2. Well, the reason that they picked 5/2 is because 5/2 minus 2, or 5/2 minus 4/2, is equal to 1/2, and log base 1/2, so log base 1/2 of 1/2 is 1. Okay, so that means we have 5/2, comma 1. So 5 over 2 is 2.5, comma 1. So we have a point right here at 2.5, comma 1. And then if I plug in 4, well, 4 minus 2 is 2, so log base 1/2 of 2, well, I know that 2 is the reciprocal of 1/2, so that must be negative 1. Okay, so 4, comma, negative 1. Okay. I have a vertical line x equals h, so remember this is in the form x minus h, so that means that my h must be equal to 2. So x equals 2 is my vertical asymptote, so I have a vertical asymptote here at x equals 2. Okay, so my curve starts just to the right of the line x equals 2. So remember, this is an asymptote. It approaches but doesn't touch, and then curves just like that. Okay, so it moves down. So it starts just to the right of x equals 2 and moves down. Okay, so the domain is everything greater than x is greater than 2, because that's my h, and the range is all real numbers. Okay, and now for b, we have y equals log base 2 of x plus 1 plus 2. So now I've got two different shifts going on. I have, remember this is written in x minus h, which means that my h is actually equal to -1, so I've shifted to the left one. And my k is equal to +2, because remember it's in plus k. So my k is equal to 2, so I'm going to shift up 2 and to the left 1. Now if I just plot some points here, so if I plug in 0, that would be log base 2 of 0 plus 1, which would be 1, plus 2. Well, if I take the log of any base of 1, I get 0, and then 0 plus 2 is 2. And then if I plug in 1, well, that gives me log base 2 of 1 plus 1 is 2, plus 2. Log base 2 of 2 is 1. That's one of our specials. 1 plus 2 is 3. Okay, so I have 0, 2, and 1, 3. Okay. My vertical line is at x equals h. My h is -1. So x equals -1 is my vertical asymptote. Okay. And then from left to right, I draw a curve, starts just to the right of the line x equals -1. Okay, and moves up. Okay, so again, I approach, but I don't touch my asymptote. Okay, and then it starts to kind of taper off, but it keeps going up into infinity as it goes to the right, and down to infinity as it goes to the left. So the domain is x is greater than -1, because it's only to the right of -1, and the range is all real numbers. Okay, and that takes care of all of our basics for logarithms.